There are many applications of periodic functions and sinusoidal functions in particular. Some of these include problems involving tidal and lunar cycles. There's others are problems involving circular motions, such as the position and movement of a Ferris wheel. And others are problems involving respiration, heart rhythm, etc., etc. All of these problems involve using your knowledge of sinusoidal functions and trigonometry. So in this video, we're going to look at just one example of how to set up, analyze, and solve such a problem. We have an equation here that gives the depth of water in meters at an ocean port at time t in hours. And the equation is given, and h is isolated. That's going to be our vertical axis. H is in meters, and our t is our horizontal in hours. The horizontal axis is like our angle. Our angle t is being sined, t being in radians. And now let's break down all the information that our equation is giving us. So we start off with the 2.3 in the front. We know that this is the amplitude. The absolute value of A is the amplitude, so the graph's going to go up and down 2.3 units from the middle. The multiplier on our t is our B value, and we know that this affects the period. We know that the period is a normal period divided by B. If I put this B into this spot in order to calculate the new period, that would be 2 pi divided by that value. So I'm going to take the reciprocal and multiply, and I get 12.4 as the period. In other words, the graph will go through one cycle after 12.4 hours. So I'm going to put that there. Then I'm just going to scale my axes to represent the other major points on my sine graph in between. We know that there are 4 of them. So if the period's 12.4, the halfway point is 6.2, and halfway there is 3.1, and so every jump is 3.1, making the third one 9.3. Alright, our next parameter is c, t minus c, so that's telling us that the graph has been shifted horizontally 1.2 units to the right. We will come back to that in a moment. And the last number here is the vertical displacement, which tells me my graph is being shifted upwards 3.9 units. Now I'm going to bring that in because that's kind of the middle of my graph, as I know. So let's make this 3.9, and I'm going to dot in what I consider to be my new horizontal axes. Now that I have the middle in place, we know that we can go up and down by the amplitude from 3.9. So if I add 2.3, I'm going to land at 6.2, and if I go down, I'm going to land at 1.6. Alright, so let's just sketch in our sine graph. A sine graph, remember, starts at the origin, goes up and back like so, and this is our new origin. So our graph is going to look up, back to the axes, down, and back to the new middle. So our sine graph for one cycle is looking like that, but we have to remember that we haven't yet applied the shift horizontally 1.2 units to the right. And 1.2 units is about right there. And so what I need to do is take this graph and shift it 1.2 units to the right. So there's one cycle of what's going on with the tides. If I wanted to extend my graph, I could. And just to make this less confusing, I'm going to take away the blue graph just to focus on my main graph. So I can certainly graph my equation for this practical situation by hand, but I'm going to use the calculator to confirm this, and then also to do some more sophisticated calculations about this situation. Alright, so let's type this equation in. Let's just erase that so we can see the equation. And we're going to go 2.3 the sine. Now be careful here that all of this 2 pi up to the end of this bracket here gets within the domain, or within the interval of the sine here. So I'm going to bracket 2 pi times x minus 1.2 divided by 12.4. All of that's within the effect of the sine. Add 3.9. And before I bring up my graph, let's just scale the window dimensions so that we can see pretty much what we have here. So on my window dimensions, I'm scaling horizontally from, let's go a little bit less than 0. Let's go from -2 up to, let's go 15 hours. And our little scale markings, they could be the 3.1s if we want. And then horizontally, and then vertically, we want to be able to see from 1.6 to 6.2. So let's go from a little bit below the horizontal axis to up to 10. And my graph should look similar to what I have on paper. And it does, so we're good. Alright, let's use this now to answer some practical questions about this situation. The first one is, what is the minimum depth of the water during this 12-hour period, 12.4-hour period, and when does this happen? Well, I can see just from my hand-drawn graph that the minimum water depth is here, and this is occurring at this time value right here, which should be a shift of 1.2 units over from the 9.3. So 10.5, and then the minimum depth of the water should be 1.6, so I can just see that from my hand sketch. On my calculator, I can simply take second function trace, which is this menu, go to minimum, and let's focus in on the lowest water depth right there, coming from the left, coming from the right, and getting a guess to be 10.5. So the time is 10.5, and the minimum water depth y, which is our h, is 1.6. So the minimum depth of water happens at 10:30 a.m. because that would be t equals 10.5 and is 1.6 meters in depth. So at 10:30 a.m. we're at low tide, and then we can see from the graph that the tide's starting to rise. The next question is, what's the depth at 1:30 p.m.? So 1:30 p.m., remember, because time is on the 24-hour clock here, we're going to continue to go 13, 14. 1:30 p.m. would be equivalent to 13.5 for t. And so what we need to find is the height of the water at t equals 13.5. And this is a perfect situation for which to use the calculator. Trace 13.5, and the depth of the water at that moment in time would be 3.78 meters. So now the question is reversed. We want to know at what time is the depth of the water 5.7 meters. Well, again, on my hand sketched graph, 5.7 meters would be right around there. And if I sketch across, I can see that there's a bunch of times when that happens. But let's use our calculator because we can get this more accurately. And we're going to do this by setting our equation equal to 5.7. In other words, we're trying to find the values of t that make h 5.7. So we're solving a trigonometric equation. This would be a rather nasty one to solve algebraically, so let's use the calculator. And we know that the first coordinates of the point of intersection give us our solutions. So I'm going to use my intersect button. So I have t equals 2.97. I think I'm going to need to store that number for use later, just in case. Let's do that. So store it in A. T equals 2.97, on and on and on. My other point is 5.63 rounded. Again, we're probably going to need that number again, so let's store that. Store that number in memory location B. Now you'll notice that the question says to find all times during the day. The two times that we found so far are in the morning, because we're at just before 3 a.m. and just before 6 a.m. But the graph is going to go down and then come back up and hit 5.7 again. So what I'm going to do on my calculator is I'm going to extend my values of t for the 24-hour period. Let's go to 25 hours. And indeed we can see that there are 4 times during the day when the depth of the water is going to reach 5.7 meters. So let's just take this down here and finish this question off. As we've talked about before, the main two solutions we need to get from the calculator in particular are the first two, because we know that the answers after that are related by one period. So if this is 2.97 and this is 5.63, then the next answer is one cycle or one period away. And this one is one period away from this one. So to get the other two answers that I need, I simply have to add on the period, which is 12.4. We calculated that above. So if we add our period to this time, we're going to get 15.37 on and on and on for hours. And if we add 12.4 to this one as well, our time later in the day is going to be 18.03, on and on and on and on. Now, those are the 4 times within the 24-hour period when the tide reaches 5.7 meters. Let's just turn our times into some user-friendly clock times. So, for example, 2 something a.m. So let's do each of these. This is going to be 2. Remember that on my calculator I had this value stored, the 2.97. Let's take off the 2 because we know that's 2 a.m. And we have 97% of an hour. So in terms of minutes, 97% of 60 minutes would be 58. So we're actually talking about 2:58 a.m. Let's do this one. We know that this is going to be 5 something a.m. Let's take the 0.63 and convert that to minutes. Let's bring up my stored B value. Take off the 5. 62% of 60 minutes makes this 38. So at 5:38 a.m., our tide's at 5.7 meters. Now to get the other two, I can convert those in the same way. But remember that 12.4 hours is 12 hours and 40% of an hour. So 40% of 60 minutes would be 24 minutes. So we could also just add 12 hours and 24 minutes to this, which would mean that this is 3:22 p.m. and this would be 6:02 p.m.